and we will talk about Dжилберта-Штейнера problem tell us that the ramification in the planar Dжилберта-Штейнера problem has a degree less than or equal to 3.
Yeah, thank you, Vasily. Happy New Year to everybody. It is nice to realize that people are interested in some mathematics even on vacations. My talk concerns a very specific type of geometric optimization problem, which is related in somehow mix of two more famous problems from which I start. First of all, call about optimal transportation. One moment. Sorry. Computer is very difficult. To be solid. Very let me see why it is so. It's not seeing good enough, yeah. Not perfect still, so maybe I should change it. Why it is so? This was sorry. Раз, ручка. Так. Why this always so difficult? Well, it was better, right? Oh, it is also one to say. Okay, well, I think is less almost seen, right? What is optimal transportation problem? So we have a set of goods which is somehow distributed in a metric space, and we want to move it to some places, and we want to do it minimizing the cost. What does it mean mathematically? So we have two measures which correspond to initial distribution of foods and the desired distribution of foods. So we have two measures in a metric space. Let these measures be probabilistic, so that mu of x equals mu of y equals 1, and suppose that they have finite support, y of y of x also. They have finite support. So each of them is a finite combination of delta measures at some points. What is the optimal transportation problem? We want to represent the difference as a sum of measures of such kind, cxy times delta x minus delta y. And want to minimize the cost. The cost is sum c, so absolute value of c, times distance between x and y. It means that moving 1 kilogram per 1 meter costs $1, and we here we move not 1 kilogram but cxy kilograms from x to y, and we want to pay the minimal number, the minimal cost. It is an optimal transportation. It is also called as Monch-Kantarovich problem.
So what is so which one the distance and which one is the cost?
So rho and g are the same.
Okay.
So, d is the distance, and
Okay.
this is the cost of this. This is called plan. In Kantarovich used economic terminology. It is plan. How we move goods from new to new. And this is the cost of the plan, and it has to be minimized.
So so excuse me, C is the cost, or C is the coefficient, just the coefficient?
Yeah, this is the coefficient. So we consider all possible representations of the difference of these two measures in such form. So C is how many goods we move from X to Y.
Okay.
Yes.
Okay.
And for this, we should pay this value.
Okay.
So, and we may move the costs from mu to nu differently. For example, if mu has 2 points, supported 2 points, and y, this is mu, this is nu, we may move this way. Imagine that we have measures 1/2 in all these 4 points. We may move this way and we may move this way. Yeah, so, and in general, there are many ways to move. For example, we may take part of goods from here, move them here, part of goods here, also move here, and so on. And we know in terms of matrices, it means the following. We have matrices for which we know the row sums, we know the column sums, and we want to minimize such a value as the sum of entries times this coefficient. This is the distance between corresponding points. Okay.
Okay.
Well, let's try to proceed. Sorry. Something goes wrong. One moment. Okay, well, let me proceed. So the second problem which we consider is the Steiner problem. It is the following problem. Again, we have a metric space. But now it is not just a metric. Well, okay. Let us formulate in the most abstract terms. We have a metric space X. We have a finite set A. And we want to find a connected set which contains A such that perimeter of C is minimal. Perimeter is a one-dimensional Hausdorff measure. Usually X is RD with usual metric. I think everybody knows how to solve this problem if A contains 3 points on the plane. Yeah, so what is the finite length connected set which connects 3 points and has minimal perimeter?
Well, if one angle is greater than 120 degrees, then just two edges. Otherwise, we find a point inside with 100.
Yes.
Yeah.
Oops. So in general, yeah, it is either such a tree with angles. They are not 120 degrees, but forgive me. Such a tree, if such a point exists, and if such point doesn't exist, it means that this angle is one of these three angles of this triangle is greater than greater or equal 120 degrees, then we just take these two sides as drawn. And it is interesting fact that in general, set which connects A in RD may have branching, like on this picture. So this is a branching point, but degree of branching is always at most 3. And also, if we have degree 3, then the points are coplanar and these angles are equal to 120 degrees. So only such branching is possible in any dimension and for any finite set A. For example, if you have a regular tetrahedron in R3, the optimal tree is not its center connected to the vertices. It is Steiner's tree for one facet and then altitude. Let me draw it by red. This is the Steiner tree for a tetrahedron. So there are 4 of them. It is not unique. Okay. And what we consider is a Gilbert-Steiner problem, which is a mix of these two. I see that red is better. I finally found necessary setting. Gilbert-Steiner problem. It is the following. We again have 2 measures, probabilistic in a metric space. And we want to represent their difference as a sum minus 1 moment. Here we may use additional points, not only in the support, again with finite support. With not finite support, it also can be considered, but there are some technicalities, and that's not what we are talking about. That's, I would say, another science to deal with such technicalities. Okay, and mu minus nu must be represented as the sum. And what have to be minimized is the following. Now we say that moving weight of, say, m kilograms by distance d is not proportional to m times d. It is proportional by m to p times d, where p is less than 1. What is the sense that it have some practical meaning? For example, you know that moving 2 elephants from India to Russia is more expensive than, less expensive than twice moving 1 elephant, right? It is quite natural. So this is the idea. So we want to minimize such a sum d of xy times cxy to p. And again, we can use additional extra points. For example, we may use some hub here. So we collect some goods and then we move them to another point. It is not infinite, right? It is not good. Well, okay. Well, let me formulate. So I use different pictures. So the theorem by Danilo Cherkashin and me is the following. On the plane, branching in Gilbert-Steiner problem, have always degree at most 3. So such hubs where you collect some goods, for example, from 3 points, and then you move them here, or maybe you collect goods from 2 points and then move them to 2 points, they are not allowed. This is not optimal.
Excuse me, am I right that the Steiner problem is a partial case of the first problem you mentioned of optimal transportation, or
No,
not?
no, I don't think so.
Okay.
In Steiner problem, you say that it must be connected. It is connectivity, some topological property. I don't think that it is a partial case.
Okay.
Okay, and it is interesting, at least it was unexpected for me, that it is related to so-called totally positive functions, to analytical issue due to Schoenberg of early 20th century. But well, let me start before we pass to Schoenberg science. Let me start with the following observation. I write W of M instead of M to P because theoretically you may be interested in problems with different weight functions, and it also may have some applicable sense. So let it be just some function W. And it will be seen which properties it must enjoy and why M to P has such properties. Because it P is between 0 and 1. Let's try the following. For example, we have such a branching that some point collects let it be triangle ABC. Some points A and B collects goods, and from A to B you move M1 kilos. From here you may M2 kilos. And actually here we may withdraw arrows and think that M1 and M2 are positive, but actually you may also think that M1 is negative. It corresponds to the arrow to the opposite side. And well, consider the triangle on some possibly different plane with such sign. W of M1, W of W of M2, and W of M1 plus M2. Actually, if such triangle doesn't exist, then simply a problem is not very interesting because, for example, if this is greater than sum of these two, then it is not interesting because you never should use weight M1 plus M2 because it is cheaper to use twice M1 and M2. Yeah, so it is doesn't have economic sense, but this function enjoys the properties that this triangle exists. For every signs of M1 and M2. and it is not hard, but we will prove it and even much more a bit later. So now just believe. Okay. Then this external angle denoted by pi. Then if this is optimal, even locally optimal, so cannot be improved, then angle ABC is at least pi. Right? Yeah, I think so. Let me explain why is this. It is not really hard. Denote these angles by alpha and beta. Then if you put an altitude here, you see that this is W of M1 times cosine of alpha plus W of M2 times cosine of beta, right? Phi is alpha plus beta. And assume that angle ABC is less than alpha plus beta. Then we can draw array here so that this angle is less than alpha. I always forget. Yeah, I think this is less than alpha, and this is less than beta. And we try to replace AB and BC with such movements by, let me use red, by the following. So we, instead of moving M1 directly to B, we move M1 to this point P. Then here we move M2 to this point P, and here we move M1 plus M2 to B. Okay, and this direction is so such that this angle is less than alpha, this is less than beta, and the length of BP is very small. And then let's see how the total cost changes. Well, let's see. What is the change? What we call delta. At first, we have new dp times weight of M1 plus M2. Okay, this is okay. Also, the distances AB and AP. What is it called? Small picture. That is a small number epsilon. This is angle phi. Then d2 is approximately d1 minus epsilon times cosine of phi, because d2 is it means that this sign means that plus O small of epsilon, so that's the derivative. That's simply because d2 doesn't differ too much from the projection of d1 to d2, because in this projection differs by this, which is epsilon times cosine of something like phi. Okay, so we have minus dp times w of m1 cosine of something less than alpha, right? And minus bp times W of M2 times cosine of something less than beta. Compare with this. And this cosine is greater than cosine of alpha, thus this is negative. After such replacement of B to P, we replace 2 segments to 3 segments, but the total change of cost is negative. So it is better to do this. Okay, so we remembered this property, that the angle is at least this angle. Okay? And that's what I say now was known for long ago. It is not our know-how at all. Okay. Is it okay? May I proceed?
Sure.
Great. So okay. Then I recall the following also quite standard lemma. Lemma is the following. So assume that A1, A2, AN, A1, is an arbitrary polygonal line in RD, closed. In arbitrary Euclidean space. Then sum of such angles indices are cyclic. So we have AI plus 1, AI plus 2. Sorry, pi minus this angle. Sum of external angles is at least 2 pi. That is a generalization of the fact that for a convex polygon, the sum of external angles equals 2 pi. Okay. And this is less or more the only equality case. Well, how do we prove it? And how we also need equality case. It is crucial for us. The equality case is actually planar. Planar and convex, like this. How to prove this? We may do the following trick. We consider random direction u on the sphere. Random with respect to uniform measure on the sphere. Okay? And consider such events. EI is that u times AI is maximal of u times a j. So that this function is maximized at index y. In other words, in this direction, if it is, for example, vertical, AI is the highest point. Okay. Of course, however you choose u, at least one event holds. That's the sum of probabilities of pi is at least one. Okay. On the other hand, we consider another event qi. It is the following event: u times ai. It is maximum of not over all indices, but only of indices I minus 1, I plus 1. It means that the point AI is higher than its two neighbors in our polygonal line. Of course, probability of qi is not less than probability of pi, because if this event holds, then this also holds. But for qi, we may calculate probabilities. Is probability, yeah, because it just means that what do we have? We only have only two vectors, this and this. And we care about directions which form obtuse angles with both of them, right? If this angle is phi, it is exactly p minus phi divided by p. It is seen because it's the set of directions. It is the intersection of two half planes. Yeah, and with the diagonal angle between them, pi minus phi. One moment. I want here 2 pi. Here I say that this probability is at least 1. Maybe it is 2 pi. One moment. Yeah, I think it is 2 pi, yeah, because even the probability that this point is higher than this is only 1/2, so it must be always less than 1/2, yeah, so I think this denominator. Okay. Yeah. So we have that sum of these guys is at least 1, which is equivalent to our inequality. Okay. Well, very good. We need this lemma, and also that for non-degenerated case, for example, if the points are not coplanar, it doesn't hold. Equality doesn't hold. Okay, so how is this all related to each other? Let's see. Imagine that we have a point where is some branching of degree at least 3. So if I draw arrows here, but as I recall, we may consider negative masses. So this is M1, M2, and so on, Mn. Moreover, some of them must be negative because the sum is 0. Because I consider branching in an extra point. Yeah, so totally this point must cancel. Yeah, we may use it as a hub, but after all, no good should remain here. Well, then we want to embed the real line to some Euclidean space. Actually, we embedded to Gilbert space, but because we need only finitely many points, it is always in some finite dimensional subspace. So let this still unknown embedding, which is already related to Schoenberg, denoted by, say, theta, we consider such a point, theta of m1 plus m2 plus mi, where I equals to 0, 1, and so on, n minus 1. And we note that if we consider this periodically, then since the sum of masses is 0, then theta, let's denote this point an, ai, then an equals a0 and so on. So it is true. Okay, and what we need, it is that the distance between ai and aj equals W of, I recall the W if the in Dжилберта-Штейнера problem is this function. W of the difference between 2 points. So if you want to write it in terms of embedding theta, then it means that theta of A and theta n of B, it must depends only on A minus B, and it depends as W of B minus A. Okay. Then imagine that such embedding exists. Then how do we proceed? On the plane, these segments which go to 1 point then form some angles. Here we may denote that phi1, phi2, and so on, phi n. And the sum of them equals 2 pi. Actually, of course, sometimes so one of angles is greater than pi. Then if you consider the real angle between these two segments, that it is less, so it is, strictly speaking, at most 2 pi. It is okay. Yeah. And I want to say that phi is at least pi minus angle a I minus 1, a 1 plus 1. Yeah, because what is this triangle? Look at this triangle. AI minus 1, AI, this triangle. What are its its length. This is W of mi. This is W of mi plus 1. And this is W of mi plus m plus y plus 1, all right? So by our the very first lemma, this angle phi must be at least this external angle. Yeah, so this is the initial lemma. And if we sum up these inequalities, then we get that sum of phi is at least sum of these guys, which is at least 2 pi. And we know that usually, if they are not complanar, this is strictly greater. And they are not complanar, it is a property of our embedding, if n is at least 4. So these status don't lie in one plane, they are in general position. Okay, so once we find such embedding of the real line to Gilbert space, we are done, right? Because everything works smoothly. We have these bounds from angles from below. We know that this sum of angles is at least 2 pi, and they are usually even greater. And on the other hand, this sum of angles is at most 2 pi. Okay? Can I proceed? Any questions? Okay. Then now I explain an embedding of R with such distance to Gilbert space. The embedding is the following. Consider such functions theta of t equals e to x minus 1. We want this function to lie in L2 by some measure, where lambda is a measure on R plus. And the lambda must be chosen so that this function is square summable. Then the distance of theta of t minus theta of s equals the norm of e to x minus t sx equals the norm of e minus s and x minus 1. It is nice that it depends only on t minus s as we need. Yeah, so we want this just to be equal to t minus s to p. Yeah, if we find such measure that this norm in L2 with respect to this measure equals to t minus s to power p, we celebrate. Okay. And actually such measure exists. Let us see. Consider the measure with such a weight x to some power minus alpha dx. For which alpha does this function belong to L2? Yeah, so we want to integral of e to x minus 1 square x to minus alpha dx be finite from 0 to infinity. On infinity, it means that alpha must be greater than 1. At 0, it is about x, right? So it means that 2 minus alpha must be greater than minus 1. So 3 must be greater than alpha. Okay? So for such alpha, this integral converges. And what is the norm? Integral from 0 to infinity e to x minus 1 square x to minus alpha dx. We just make a change of variable. Tx is tau. It is integral from 0 to infinity e tau minus tau right minus 1 square tau to minus alpha minus 1 minus alpha plus 1. It's very difficult. Right tau, sorry. Right x equals tau over t, right? Then tau t is to the power alpha minus 1. Yeah, tau to minus alpha d alpha. This is the only factor which depends on t, so it is some constant depending on alpha, of course positive, times t to alpha minus 1. So if alpha minus 1 is to p, and it is quite possible because alpha minus 1 is between 0 and 2, and 2p is also between 0 and 2. Then we get that it is some constant times 2 to t to p. So it is the square of the norm, so the norm itself is proportional to t to p. So it remains to divide by this coefficient of proportionality to get this equation. And that's the Schoenberg construction of the so-called metric definite functions, or like that. I don't remember the exact terminology, but it is intimately related to the theory of Bochner of positive definite function, which are such functions that the kernel f of t minus s is positive definite. So all minors of corresponding matrix are positive. Okay, so I think that we proved everything. So that the main theorem is proved. And a couple of words, what to do next. It was all on the plane. It is interesting that in R3, branching of degree 4 is possible. It is interesting because for usual Steiner problem, we know that it is impossible in every dimension. This said, it remains a major question, which branching is possible in AD. We actually know almost nothing about that, except dimension 2, and that in dimension, that the answer is not trivial, that in dimension 3, it can be greater than 3. Okay, that's, I think, all that I wanted to say, and I will be happy to answer your questions.
Hello, Vasilovich. Where are you?
Yeah.
Thank you very much. Are there any questions or comments? Okay. Sherry, excuse me. Maybe we'll wait Vasilovich a little bit, and yeah, then we can finish.
Yeah, thank you.
Thank you very much.
Bye.
Bye bye.